Welcome everyone to a new lecture on symmetric cryptography and message authentication codes. Before I start, I just wanted to apologize for my voice as I'm recovering from a cold. Here is the outline of the lecture. I'm going to start defining some terms, and then after that, I'll talk about some examples of symmetric cryptography. I'll start with the very simple one, which is the Caesar cipher, and then after that, we're going to talk about the Feistel cipher and the two very important implementation of Feistel cipher, which is DES and AES, data encryption standard and advanced encryption standard. And I'll talk about their differences. You will see that which one is stronger and which one is easier to compute. And at the very end of this lecture, I'll talk about message authentication codes. All right, so let's get started. When we talk about cryptography and encryption and decryption processes, there are a number of terms that we need to understand. The two very important ones are plain text and ciphertext. Plain text is the original message that we do not want to send it as is through an internet connection or any other network connection, because when you do that, um, some middleman can sniff the packets at the middle of the way, and the confidentiality of the message can be threatened. In order to preserve the confidentiality of your message, you will encrypt it and convert the plain text to ciphertext. That's called the encryption process. And the ciphertext is basically the coded version of the original message. And the receiver of the message, after receiving the ciphertext, it needs to understand what the ciphertext means, so it needs to convert the ciphertext to plain text. That's called the deciphering or decryption process. So remember the two um, other alternatives for encryption and decryption. Encryption is called enciphering, decryption is called deciphering. So cryptography schemes are generally divided into two classes or two groups. The first group is symmetric cryptography, and the second one is asymmetric or public key cryptography. In this lecture, we only focus on the symmetric cryptography or secret key cryptography. In this type of cryptography, as you can see here, the plain text, which is represented by variable x, um, will be converted to the ciphertext, which is represented by variable y. And in order to do that, we're going to apply the encryption algorithm, which is here, which is represented by the function e here. Function e gets two input parameters. The first one is the key k, which is a shared piece of information that is, or I should say, it's a number or a piece of information that is shared between the receiver and sender, because it's used for both encryption and decryption process. And the second parameter of this encryption function is the actual plain text, and this function will return y. So when I want to make sense out of this equation, I can either consider e to be a programming function, or I can consider it to be a mathematical function. Normally, because cryptography is full of math, because you have to create a very secure um, function, and it should be proven to be secure using math. Because it's all about math, these functions are not quite programming functions. These are mathematical functions. And But it's not wrong if you say E can be a programming function, and then that's considered to be the encryption process. There are a lot of encryption algorithms. We look at DES and AES in detail in this lecture, and after we want to decrypt the message, we will apply another function on the key and the ciphertext. The function here is represented by D. That's the decryption function. It is applied on two values. One is the same key that we used in the encryption process, K, and the other one is the ciphertext, which is, the value that the receiver receives, and this is going to return X. Now, if I say this, E sub K equals basically E of K and X, or I should say, EK of X is equal to E of K and X, and dk of X, or I should say Y here, dk of Y equals d of K and Y, then it's easy to see that basically E K of dk of Y is equal to Y, right? Just you need to plug in the values, and that's going to be the case. Or you can say dk of ek of x is equal to x. When you have two mathematical functions like d and e, or dk and ek, the reason I put k as a subscript is because I didn't want to have a function with more than one parameter. That's harder to address in math. So when you have a situation like this, when you apply two function on a value and you get the same exact value, that means these two functions, d and e, are the inverse of each other. So that means dk is equal to ek inverse, or you can say ek equals to dk inverse. In order to show you even better and make it easier to understand, assuming that this is the domain of all the plain text, and this is the target, which is all the set of all ciphertext. You can say if you have a plain text here, and if you have a ciphertext here, using E or E sub K, you can go from P to C, which means you can convert a plain text to a ciphertext. And let me use a different color now. Let's use a black color. Now, if I want to go back from C to P, I should use a decryption function, but it should be exactly the reverse of EK. And that's how symmetric cryptography works. So far, we have learned that in order to use symmetric cryptography, we need to share a key between the two parties that are involved, the sender and the receiver, or the encryption party and the decryption party. In order to do that, normally the key is sent through a secure channel that is secured in a way other than the symmetric encryption, because that secure channel should exist before you start the symmetric cryptography. Sometimes this secure channel is created using public key cryptography, which we will discuss in the future chapters. Before we start talking about the modern symmetric cryptographic algorithms, let's talk about a very simple example of them, which is the Caesar cipher. And I'm going to explain that using a very simple example. As you see here, if the plain text is meet me after the toga party, the cipher text looks like this. If you draw a line between every corresponding letter of the plain text and cipher text, you understand how it works. M is mapped to P, E is mapped to H, E is mapped to H, T is mapped to W, M is mapped to P, all the way to the last one where Y is mapped to B. If you consider the way these letters are mapped to each other from plain text to ciphertext, you will, if you think about it, you will realize how the relationship between them. So this is how they are mapped to each other. Basically, if you write down all the letters of English alphabet from A to Z, let's say W, X, Y, Z, and write down again capital letters of the alphabet from A to Z, you will see that you will see the the relationship. Basically, let me write down D, E, F as well. So A is mapped to D, B is mapped to E, C is mapped to F, W is mapped to Z, X is mapped to A, Y is mapped to B, and Z is mapped to C, because every letter in the alphabet is mapped to the letter standing 3 positions further in the alphabet, like A to D and B to E. But when you reach to the final letters X, Y, Z, you need to wrap around the alphabet and say, for example, X is mapped to A, or Z is mapped to C, right? So that's how Caesar cipher works. In order to summarize how Caesar cipher works, we can use a mathematical notation for them. Assume that every letter in the alphabet from A to Z corresponds to numbers from 0 to 25, because there are 26 of them in total. And if you think so, I mean, if you do this conversion from letters to numbers from 0 to 25, then what we can do is we can say the encryption algorithm of Caesar cipher on a given key, which was 3 in the previous example, and on a single letter P would be equal to P plus K mod 26. Mod 26 is because we're going to wrap around the alphabet. After we reach to Z, we're going to go all the way back to A. So that's why we do mod 26 at the end. And the decryption algorithm will get a single cipher letter and convert it to a single plain text letter by doing this: subtract K from C and do mod 26. But just remember, the negative number, the mod of a negative number, let's say if C is 0 and K is 3, 0 minus 3 is negative 3. Negative 3 mod 26 is not negative 3. It's not the programming mod. It's basically the mathematical number theoretical mod, which is equal to 23. and 23 represents X. So for example, if the cipher letter is A, then the plain text letter would be X, because -3 mod 26 in number theory is equal to 23, not um, not 20, not -3, which is basically the way programming languages like C and Java work. Before I start talking about the modern symmetric cryptography examples, we need to know that there are two types of these algorithms. One is the stream cipher, and the other one is block cipher algorithms. The block cipher algorithms are more common, and we will see the examples of block cipher algorithms in this lecture. But I just wanted to say that it is possible to have a stream cipher, which basically uses some algorithmic bit stream generator to convert a stream of zeros and ones in plain text to a stream of zeros and ones in ciphertext. That's the encryption part, and in the decryption part, we do the opposite task, which means every bit of ciphertext will be converted to a bit in the plain text. But the block cipher algorithms will encrypt a chunk of plain text with size, with a specific constant size, let's say b bits, and that's going to create a b-bit ciphertext, and the ciphertext chunk with b-bits will be decrypted into b-bits of plain text in the decryption algorithm. In order to understand the very first modern cryptography algorithm, or I should say symmetric cryptography algorithm that we're going to see in this lecture, we need to understand the Feistel encryption decryption mechanism. And if we understand this, the DES would be a special case of this one, or it's going to be like a variation of Feistel encryption decryption algorithms. So let's first look at this mechanism. The idea of Feistel encryption algorithm is to convert a plain text that you see on the top to a ciphertext that you see on the bottom with the help of a number of subkeys, which you see here, K1, K2, all the way to K16, which are all derived from a single key that is shared between the encryption and the decryption algorithm. So that's the goal of the encryption algorithm, and the ciphertext should be in a way that if someone does not have the key and therefore does not have the subkeys K1 to K16, it would be impossible to reconstruct the plain text given the ciphertext, or even to create a ciphertext from the plain text without the key. So having no key makes it either impossible or very difficult to convert plain text to ciphertext, or vice versa, ciphertext to plain text. And in the decryption part, as you see on the right hand side of the picture, on the bottom we have the ciphertext, on the top we have the corresponding plain text, which should be the same as the original plain text that was encrypted. Again, the decryption algorithm uses 16 subkeys K1 to K16, which are basically all derived from a single key shared between sender and receiver, or encryption and decryption mechanism. And same story. In order to retrieve or in order to obtain the plain text, you need to have both the ciphertext and the key. If you don't have the key, you only have the ciphertext, reconstructing the plain text should be computationally infeasible, which means it should take a very, very long time. And in order to make sure that this mechanism is safe, the Feistel encryption and decryption algorithm will happen in 16 different rounds. In each round, the input comes from the previous round and the output goes to the next round as an input. So I have summarized the functionality of encryption algorithm in these recursive relations that you see. First of all, let's say you have a plain text or you have a chunk of plain text, like B bytes of plain text, which is sitting on the very top right here. Then you break this into two equal halves, left hand side and right hand side. I'm going to call this LE and the right hand side is RE. The E stands for encryption, left and right. L and R are basically left and right. And then that's going to be the input of the very first round. Each round, or let's say the ith round, works in the following way. The output has two halves, the left half and right half. The output of the left half of the output is equal to the right half of the input. So LEI is equal to REI minus 1 for every I from 1 to 16, for every round, from round 1 all the way to round 16. And the right hand side of the output, which is REI for the ith round, has a bit more complex formula, is equal to the left hand side of the input, which is LEI minus 1, exclusive or I should say bitwise exclusive or by another value. This value is basically a function of ki. I forgot an I here. It's a function of ki and Ri minus 1. What is ki? I'll show you an example of how to implement Feistel using the AES. But for now, just think of ki as a subkey, which can be derived deterministically from the actual key. And this function also is a function that is deterministic, which means if you know the formula, you can just plug them in, plug ki and Ri minus 1 and get the return value of function f. And the return value of function f will be XORed with the left hand side of the input for the ith round to create the right hand side of the output for the ith round. And eventually, when you reach to the end of the 16th round, all you need to do is to swap the left and right hand side. So the ciphertext is obtained by concatenating the left hand side of round 16 to the right hand side of round 16 output, but in the opposite order. So first the right hand side concatenate with the left hand side, and this is going to give you the actual ciphertext at the end. And it's easy to see that if you do this in the opposite direction, that would be the formula for decryption, because remember, decryption algorithm is the reverse of encryption algorithm. So I don't want to mention that. You can just check out how decryption works, which is very similar to the encryption but in the opposite direction. All right, so the most well-known implementation of Feistel algorithm or Feistel mechanism is DES, or Data Encryption Standard, which was very popular before, but now because of the enhances in computer technologies and the way computer performance has increased substantially, DES is not secure anymore, so we don't use DES. But it's important to understand it in order to understand um, other symmetric cryptographic algorithms. So uh, let's take a look at how DES works. DES stands for Data Encryption Standard. Uh, Basically, it's an implementation of the Feistel algorithm, which I showed you in the previous slide, with some changes. The original Feistel didn't have this step of initial permutation and the final step of inverse initial permutation, but the DES has. But other than that, the rest is pretty much the same. In each round, as I showed you earlier, you need to break the input of the of each round to two halves, and then apply a function called f and the exclusive OR to create the output. And I'll show you the more details of DES in the next slides. But what's important in this slide is the way the key, which it has, in this case 64-bit length, is broken into 16 subkeys. We have multiple boxes which represent functions that are applied to the key to create the subkey. First, the very first one of them is PC1, or permuted choice 1, which basically gets rid of the parity bits of the 64-bit key to create 56 bits. I'll talk about this later. And then using left circular shifts, either 1 bit or 2 bits, and then applying another function permuted choice 2, we create all the subkeys K1 all the way to K16, and as you see, they're all functions of the original key K, right? This concept of creating subkeys is true for both encryption and decryption. I'm going to show you the encryption only, but you can use the same exact formula for the subkeys of decryption part, and that's the subkey generation. Now, what is PC1, PC2, what is permitted choice 1 and permitted choice 2? I'm gonna talk more about the details in the next slide. Also, I will show you the initial permutation in the next slides. Here is the initial permutation of DES, and as you remember in the previous slide, I showed you that the reverse of this permutation is used on the very, very last step of encryption. So as you see, there is some sort of pattern in the permutation of the 64 bits. Every single blue node that you see on the top show the 64 bits of the input, or shows 1 bit of the input, so you have 64 of them, so it's going to be this 64 bits of input. And every single blue node on the bottom shows the output of the initial permutation, or each blue node is a single bit of the output of the initial permutation. I mean, there's no need to memorize any of that. I'm just showing you the specifics and the details of DES. And also, this is the PC1 permitted choice 1. This is one of the blocks that I showed you in the picture that was showing the DES functionality. As you see, PC1 gets rid of bits 8, 16, 24, 32, 40, 48, 56, and 64. Basically, it gets rid of the bits with index that are divisible by 8. And these bits were previously known as parity bits. They were used for making sure that we don't lose data over a connection that can be faulty and noisy, but it doesn't happen anymore in the modern computers and the modern internet. So they're kind of useless because parity bits are redundant data and you can just get rid of them completely. There was another block called PC2 or permuted choice 2, which you can see the specifics of it here. If you remember, the input of that block was 56 bits long and the output was 48 bits long. As you see, some of the bits will get eliminated in this box. So as I showed you, DES had 16 rounds. Each of those rounds will have a circuit like this. As you see, we have some exclusive OR circuits, which bitwise exclusive ORs, the sub key of that round with half of a block that I showed you earlier in the 5-cell encryption algorithm. And also there are some S boxes, S1 to S8. You can check out the details of each box on Wikipedia. I mean, there's no need for doing that, but if you're curious and you wonder how each of these S boxes works, you can check them out. But the important point here is each of those S boxes will eliminate or will reduce the number of bits from 6 to 4, so that in total, when you have 48 bits given to these 8 boxes, the output will be only 32 bits. And that 32 bit will be used for the output of the current round. And the E here, the E block, which is basically the function used for changing half of a block in every round of 5-cell mechanism, is represented here. So this is the E block. As you see, it kind of extends the 32-bit half block to 48 bits so that it can have the same exact length as the subkey, so we can do a bitwise operation, bitwise exclusive OR operation on them. So that's kind of an extender. And this P block is going to do some kind of permutation on the outcomes of the S boxes to create the output of each round. What I'm going to do now is I'm going to show you a very quick example of how DES works. Imagine you have a hexadecimal palindrome as a plain text. This is the plain text, as you see, 02468 ACE and then ECA 86420. The reason it's palindrome is because it reads the same as forward, the same forward as backward, so it's considered to be a palindrome, but it doesn't need to be palindrome. It's just an example. And this plain text, in order to find its length, what you can do is you can consider every single digit of hexadecimal as 4 bits, because it's made of like 16 digits. Every digit is 4 bits, so the total length would be 64, and that's pretty much the same exact length for the block used for DES. And the key is also 64 bits long. In some resource, in some sources you may see the key of the AES is 56-bit long, and that's the actual number. It's not 64-bit long. Why? Because of the parity bits that I showed you earlier. You know, those parity bits can be ignored because these are redundant data that were used traditionally to uh, nullify or cancel or detect and cancel some noises because of electromagnetic waves. But now, because of the advances in technologies and the internet, those redundant parity bits are, are not used, but we're going to get rid of them anyway. But in any case, the key length is 56-bit, but we're going to add some parity bits to make the key length 64-bit. And this is, again, a 16-digit hexadecimal number, which can represent 64 bits, 4 bits per digit, 4 times 16, 64. And the ciphertext block will have the same exact length as the plain text. And in order to show you how this works, I'm gonna give you some intermediate results in the next slide. All right, so if you remember the input, which is the plain text, we use that to create this permutation, or I should say this shuffled 64-bit value, which is the outcome of the initial permutation applied on the initial plain text block, and then we break it into two halves, the left hand side and right hand side. This is L0 and this is R0, and then that becomes the input for round 1, and also the key that I showed you, the 64-bit key, will generate all of these 16 subkeys. So we have subkeys K1 all the way to K16, and with the help of K1 and L0 and R0, we create L1 and R1, which are the outcome of round 1, and then outcome of round 1 because it becomes input of round 2. With the help of those and the K2, we can create L2 and R2, so on and so forth, all the way to the end of round 16. After you reach around 16, then you apply the inverse permutation, inverse of the permutation you did initially. So it's going to be IP inverse, initial permutation inverse, applied on the outcome of 16th round to create L to create the updated L16 and R16. So we saw DES details, and we saw that it's a very complicated algorithm, and it works beautifully, and it has no security issue other than exhaustive key search attack. What is exhaustive key search attack? If a encryption algorithm or a symmetric cryptography has short key size, for example, DES has 56-bit key size, then the attackers can try all combinations of all possible keys on a given ciphertext to decipher it, to decrypt it, and that's considered to be an exhaustive key search attack. Now, if the time required for exhaustive key search attack is reasonable, then the encryption algorithm is not considered to be safe anymore. Previously, like some years ago, when the technology wasn't that advanced, we could say the time required to do um, 1 billion decryption is equal to 1 second, right? Not by normal computers, but with some like big computer, you can reach to this performance to basically decrypt 1 billion times in 1 second. If that was the case, then the time to do exhaustive key search attack on DES would be 1.12 years, which is more than a year, but it's not that long. Why? Because the total number of unique keys for DES is to the power of 56, which is 7.2 times 10 to the power of 16. Now, imagine if you use a supercomputer that can do up to 10 to the power of 13 decryption per second. Then in that case, that supercomputer can break DES key within 1 hour, because if you divide the total number of alternative keys by 10 to the power of 12 decryption per second, which is the speed of decryption by a supercomputer, the answer would be about 1 hour or 3,600 second, or in that range, right? So it's not safe. DES is not safe with the current speed of computers. So one option is to use triple DES, which uses basically 3 DES mechanisms back to back, and this will triple the size of key from 56 to 56 times 3, which is equal to 168. That's going to solve the exhaustive key search attack, because even if you have a supercomputer with this speed, 10 to the power of 13 decryption per second, it takes you 5.8 times 10 to the power of 29 years to decrypt ciphertext without having the key, which is enormous. And by the way, this is the average time, right? So if you want to get this 1 hour, for example, on the first row, you need to divide 7.2 by 7.2 times 10 to the power of 16 by 10 to the power of 13, and then divide it by 1. That's going to give you 3,600 seconds, and that's going to be 1 hour. In this case, for triple DES, it's going to be many, many years. Like, this number is astronomical, so forget about attacking triple DES using exhaustive key search. That's impossible. But the problem that triple DES has, or the drawback it has, is that it's not easy to do the encryption and decryption with the key, because I'm not saying it's not easy, I'm saying it's not efficient. You have to spend 3 times more than you spend on a DES encryption algorithm to do an encryption operation on triple DES. So it's 3 times less efficient compared to DES. That's why AES is more common than the other two, and than DES and triple DES right now. Why? Because it uses some complicated mathematical tools to make DES safer by using like a longer the key size, like 128 bits, or 192 bits or 256 bits. So it's gonna eliminate the chance of exhaustive key search, and at the same time, it won't be as time consuming as triple DES. So it has the benefits of both DES and triple DES. So let's get into the details of AES. AES basically uses 128-bit chunks of plain text to do the encryption process, and it generates 128 bits of ciphertext as the outcome of the encryption, or you can say as an input of decryption, it gets 128-bit ciphertext, and it generates 128-bit plain text blocks. So one thing that you need to understand about AES is that it's an advanced version, so it's going to be faster and it's going to be more secure compared to DES. However, it has more complicated and has more complicated operations, and it's harder to understand. So what AES does is it breaks the plain text, which is 128 bits, into 16 bytes. Every byte is 8-bit long, and it converts it to a 4x4 2D matrix of bytes. So it's going to be 16 bytes. It's a 4x4 2D matrix of bytes. And also, as I showed you earlier in the previous slide, we have three different options for keys, either 16-bit or I'm sorry, 16 byte, or 128 bits, or 24 bytes, or 32 bytes. And depending on how many bytes we have, the number of rounds will change. Here in this slide, I have shown you the detail of AES when the key length is 16 byte or 128 bits. But if the length of key increases, then the number of rounds will increase. The number of rounds becomes 12 and 14 for the mid-size and longer key length. So it would be more secure, but it's going to be a bit slower to do encryption and decryption. So as you see here in this right hand side, I have 10 rounds, round 1, 2, 3, all the way to 10. So that means I'm talking about a key length equal to 16 byte or 128 bits. So with that key, whatever the length is, AES will create multiple subkeys, one for each single round. And just like DES, AES also has like different rounds, but the operations happen in each round will be completely different than DES and will be a bit more complicated. For example, in each round it does a substitute byte operation, shift row operation, mixed column operation, and add round key operation. And these operations are not going to be operations on bits the way we saw them in DES. These are operations on bytes, and everything happens in every mathematical operation happens on bytes in each round. So that's why I said, the 128 bits becomes 4x4 to the area of bytes, and then the operations happen in each round on those 16 bytes. And just like the ES, the input of each round is going to be the output of the previous round, and the output of each round is the input of the next round. So that's how things are in AES. And also, the subkeys are 128 bit long or 16 byte long. And again, the keys will be converted to a 4x4 2D matrices of bytes. So let's take a look at the detail of each round of AES. I told you we may have 10, 12, or 14 rounds. Let's see what happens in each round. We have multiple transformations: byte substitution, shift row, mixed colon, and add round key. Let's take a look at byte substitution. We have 16 bytes as the input of this operation, and as the output we have 16 bytes. The input bytes are labeled by aij, I from 0 to 3, j from 0 to 3, and the outputs are the same, b0, bij, I from 0 to 3, and j from 0 to 3. And each aij is mapped to its corresponding bij using a function, like in this case it's shown by s, but this function is the multiplicative inverse of aij. So bij is the multiplicative inverse of aij. Is it the multiplicative inverse in the like the way we learned it in normal algebra? The answer is no. It's going to be a different math. It's not going to be the normal algebra that you have learned in your earlier education. So I'll show you a bit more detail about that kind of operation. Then we have shift row. What does shift row do? It basically shifts the bytes of rows 2, 3, and 4 1, 2, or 3 cells to the left. It doesn't do any change to the very first row, but the second row will be shifted to the left by one byte. The third row will be shifted 2 bytes to the left, and the third row will be shifted 3 bytes to the left. So A33 will be placed here, A32 will be placed here, A31 will be placed here, and A30 will be placed here. So it's a shift to the left, but it is not a very simple shift left. It's a shift left, and it rotates if you reach to the end of matrix. And also we have the mixed columns operation, which multiplies every column by a constant polynomial, and that's how the mixed column step or transformation works. And then we have add round key, which basically exclusive ORs the input by the keys in a byte by byte fashion and generates the output. All right, so as an optional part of this lecture, I'm going to briefly talk about the arithmetic operation that are used in AES, the Advanced Encryption Standard. It's not going to be the normal arithmetic that we use, normal algebra. It's not going to be normal. It's using Galois field because it's way more secure when it comes to doing encryption and decryption because of the irreversibility of some of the operations in Galois field. It's a Galois field up to the power of 8, which is 256. And the reason it's, let me first briefly explain what Galois field is. It's a finite field, which means it's made of a finite set of 256 elements. We define addition and multiplication on these elements, and the set of 256 elements are closed under addition and multiplication. But it's not going to be the normal addition or normal multiplication. We define addition and multiplication a little bit differently. In order to understand the addition and multiplication better, you need to think of the finite set that Galois field is defined on for AES purposes or AES arithmetic purposes is made of 256 polynomials. So we have 256 polynomials with the following property. Their degree is going to be less than or equal to 7, and they're all having binary coefficients. So imagine you have the following polynomial. For example, let's say x7 with coefficient b7 plus b6x6 plus all the way to b1x plus b0, right? This represents this number b7, b6, all the way to b1, b0, and this is basically a binary number with 8 bits, which is a number from 0 to 255. And that's why we say this is a special type of Galois field of with size 2 to the power of 8, which is 256. That means all numbers in this field is from 0 to 255, right? It's not like a normal algebra with infinite number of numbers. We only have numbers from 0 to 255 to work with, right? But how does addition defined in this field? Basically, the addition would be similar to the exclusive OR, because let's say you want to add these two values. By the way, because each number is 8-bit long, you can represent them with 2 hexadecimal digits. So this is one number or one polynomial, and this is another number, sorry, or another polynomial. When you add them, it's like adding these two polynomials. And when you do the addition, for example, the x will be eliminated because x plus x is equal to 2x, but the coefficient have to be binary. So because we don't have number 2 in binary, so 2 will be truncated and it becomes 0, because 2 in binary is 1 0, and when you truncate it, you just get rid of 1, and the coefficient of x becomes 0. So x plus x will give you no x. That's like a strange way of doing summation. Is kind of similar to Boolean algebra, if you remember it from your COT 3100, or if you haven't taken it, forget about it. And you can write it in binary, and that's pretty much the exclusive OR. And then you can rewrite the inputs and the output using hexadecimal. The product operation would be a bit more complex, because when you multiply two polynomials, you know what's going to happen. The extended value, or the extended polynomial, will have, because here you have 4 terms and here you have another 4 terms, the extended product will have 16 different terms, as you see here. And then when you simplify them the way I told you, you get something like this. And this number is not in the finite field that we were talking about, because the finite field only contains polynomials of degree 7 or less. The degree of this result is 13, and that's a problem, right? So in order to make the product inside the Galois field, what we can do is we can find the mod of this polynomial when you divide it by this special polynomial of degree 8. Because the degree is 8, the mod of dividing one polynomial by the other polynomial will be less than 8, which would be 7 or less, and that assures us that the remainder will be inside Galois field. And that's the unbreakable polynomial that we use for all the truncations and all the mod operations that are used in this kind of arithmetic. And when you find a mod, the result would be 0, 1. Now, how do you do the mod? It's a longer story. You need to first learn how to do the division between two polynomials, and then find the quotient and remainder as two other polynomials. As I said, these are optional parts that I won't ask in an exam, but maybe some of you are interested in understanding how AES arithmetic works, or why AES is faster than DES and also more secure at the same time. How is it possible? Well, it's possible because of all of these crazy math. All right, so next we talk about message authentication codes. I'm just going to introduce them. I'm not going to spend a lot of time on this. Basically, in order to authenticate the messages and control the internal or external errors on the messages, excuse me, what we can do is we can add some digest of message to the actual message on the source, and then see if the message digest is received in the same exact way in the destination. So let's say the message M is going to be sent by source A. So before sending, A is going to apply a function, let's say function f on M. That function can be thought of like a normal like crypto hash function, the way we saw it like in the previous chapters. And M of or f of M is going to be concatenated with M, and that's going to create M followed by its digest, and then you just send it to the other side. Now, if you want to make sure your message is confidential and is sent in a confidential manner, you can use a symmetric encryption algorithm like AES or DES, using a shared key like K to encrypt M and FM, M and F of M, M and F of M. And after encryption, you just send it to the other side. The other side, the destination will decrypt the message using the same exact key, and then it's gonna get M and F of M. If the message has not been alternated, or the message has not been altered, I should say, in the middle of the way, then the destination, in the destination, we can do this. We can apply F, the same F that source A used, on M, the received M, and compare it with the received digest, which is the received F of M. If F of received M equals the received F of M, this comparison says they're equal, then the message gets authenticated. That means the message didn't get modified or altered at the middle of the way. And there's another way of doing this. You can first apply your encryption algorithm on the message, and after you get the ciphertext, you do the same thing. You just get the digest of the ciphertext, concatenate it with the actual ciphertext, send it over in the receiving side, get the ciphertext and its digest, apply F on the ciphertext, then compare it with F of with the received digest. If they're equal, then the message is authenticated. Then you can retrieve the message by applying the decryption algorithm with the same key as the sender, to create to reconstruct the original plain text. Now, in order to make the authentication process even more secure, what we can do is we can generate the message digest by applying a function like C on both the message and uh, a key that is shared between both source and destination. So this way, the digest will depend on a key as well. And that key is shared between the source and destination. So the message will be concatenated with the outcome of C of M and K. Let's call it the MAC, and that uh, will be the message that is going to be sent to the other side. Let's say we only care about authentication, no confidentiality. So we don't encrypt it using AES or DES. We just send it as is to the other side. That's just for simplicity. And then in the receiving side, we're going to do the same exact thing. We're going to apply C on M with the same key K, and then compare the results with the received MAC of K and M. If they're the same, then the message is authenticated using the key K. Now, if you want to add confidentiality to the picture, then you can do that in two different ways. The first way will tie authentication to the plain text. The second way will tie the authentication to the ciphertext. Both of them are, fine. There's no problem with any of them. In the first approach, when we tie the authentication to the plain text, that means first we find the MAC, the message authentication code, and then we do the encryption. In the receiving side, we first do the decryption, then we compare the MAC with the digest of message. In the second approach, we first do encryption, then we calculate the MAC in the sender side, and in the receiving side, we first calculate the MAC and do the comparison, and then we do the decryption. So both of them will provide both message authentication and confidentiality. Now, one thing you need to remember is that in order to create a message authentication code, there are many ways to do that. The way that is defined in the book, that is mentioned in the book, and it's a very common and great way, is to use HMAC, which is basically using a hash function during the process of generating the MAC. And this is a very simple example of how to do this. Let's say your message is a very long message. Then what you need to do is first you break your message into smaller chunks, each one with B bits length. And then you have the key K, which can be, much shorter than the B bits packets that you had in your input, in your message. So the message was broken to multiple B bit packets, and B is, let's say, greater than the key size that you have. So in order to make the key long enough so we can work with it, we add some leading zeros. So K plus is basically the key padded by some leading zeros, so that the total length becomes B. And then we just gonna exclusive OR K plus with IPAD. IPAD is a constant number that is normally set to this number 0x3k3. I'm sorry, 363636. The number of repetitions of 36 is equal to B, because every 2 digits of hexadecimal is is equal to B divided by 8. because every 2 digit of hexadecimal is equal to 1 byte. So you need to repeat 36 b over 8 times so that the total length becomes b bits. And this iPad will be exclusive OR by the K plus, which is the padded key, and that's going to generate the very first part of your or the very first b bit packet of your message, and you concatenate that b bit with the remaining bits of your packet, and the whole thing is going to be given to a hash function, a crypto hash function like SHAs or SHAs that you have seen before, like SHA-128, 256, so on and so forth. And as almost all of the hash functions need some nonce or some random number like this. Initialization vector is the name that we give to this nonce, to this constant value that the hash function needs. And the hash function will generate a digest for SI and M, where M is your message, and this sign, the two vertical lines, show the concatenation. And then that message digest will be concatenated with the exclusive OR of the key and OPAD, which is a constant. And the exclusive OR of K plus and OPAD is called SO. SO will be concatenated with the outcome of the hash, and it creates another input for the hash function. This one is 2 times b bits long, and OPAD is basically b over 8's repetition of 8 bits, 5c. So it's like 5c, 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 5c. How many times b over 8? For example, if b is 16, then it's going to be 2 5c's. It's going to be 5c, 5c. If b is 32, it's going to be 4 times 5c. It's going to be 5c, 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 5c. And then the next part is to apply the hash function, the same hash function, on the concatenation of SO and H of SINM, and then the result will be the HMAC of key K and message M. Key K was used once here, and iPad, OPAD are constant deterministic numbers, and IV is the initialization vector that's a non-deterministic constant number. And finally, you can see the references for this lecture.